If V is a finite dimensional vector space and T is a linear operator on V, then we know that diagonalizability of T means V can be decomposed as direct sum of eigenspaces. And we made a comment before that if diagonalizability fails, then probably the eigenspaces are not big enough. So, we will see now in the second module of chapter 7, where we continue talking about Jordan canonical forms, that the generalized eigenspaces will do that job. That means we will be able to write the vector space V as a direct sum of generalized eigenspaces. And now the task is to find basis for these generalized eigenspaces, and if we can choose a basis correctly, then we will be able to form the Jordan canonical form for the linear operator. Let V denote a finite dimensional vector space over a field F. Theorem: let T be a linear operator on a finite dimensional vector space V such that the characteristic polynomial of T splits in the base field F. Let lambda 1, lambda 2 and so on lambda k be the distinct eigenvalues of T. Then for every vector V in V, there exist vectors V1 in k lambda 1, V2 in k lambda 2 and so on Vk in k lambda k, such that V is equal to V1 plus etc. up to Vk. K lambda 1, k lambda 2 and so on k lambda k are the generalized eigenspaces. Proof: the natural number k denotes the number of distinct eigenvalues of T, and the proof is by induction on the number k. Let k be equal to 1 and let m be the multiplicity of the eigenvalue lambda 1. Then T minus lambda 1 raised to m is the characteristic polynomial of T, and hence T minus lambda 1 I raised to m is 0 by the Cayley-Hamilton theorem. Thus, V is equal to k lambda 1 and the result follows. Now, suppose that for some integer k greater than 1, the result is true whenever T has less than k distinct eigenvalues. We assume that T has k distinct eigenvalues now, and let us prove the statement. Let mk denote the multiplicity of the eigenvalue lambda k and Pt the characteristic polynomial of T. Then Pt can be written as T minus lambda k raised to mk times Qt for some polynomial Qt which is not divisible by that linear polynomial T minus lambda k. Let Wk denote the range of the operator T minus lambda k I raised to mk. Then we know that Wk is T invariant. Observe that T minus lambda k I raised to mk maps k lambda I onto itself for every I less than k. For suppose that I is less than k, since T minus lambda k I raised to mk maps k lambda I into itself, and since lambda k is not the same as lambda I, it follows from a previous theorem that the restriction of T minus lambda k I to this generalized eigenspace k lambda I is 1 to 1 and hence onto. One consequence of this observation is that for I less than k, k lambda I is contained in Wk, and hence lambda I is an eigenvalue of T restricted to Wk for I less than k. Next, observe that lambda k is not an eigenvalue of T wk for suppose that Tv is the same as lambda kv for some v in wk, then v can be written as T minus lambda k I raised to mk of w for some w in v, and it follows that T minus lambda k I of v, which is 0, and that is the same as T minus lambda k I raised to mk plus 1 of w. Therefore, w belongs to k lambda k, and by a previous theorem we get v is equal to T minus lambda k I raised to mk of w is equal to 0. This shows that v cannot be an eigenvector. Hence, lambda k is not an eigenvalue of the operator T restricted to wk. We observe that every eigenvalue of Twk is an eigenvalue of T, and the distinct eigenvalues of Twk are precisely lambda 1, lambda 2 and so on up to lambda k minus 1. Now, let V belong to V, then T minus lambda k I raised to mk of V belongs to wk, and since T of wk has k minus 1 distinct eigenvalues lambda 1, lambda 2 and so on lambda k minus 1, the induction hypothesis applies. Let k lambda I dash be the generalized eigenspace for the operator T wk with respect to the eigenvalue lambda I for I equal to 1, 2 and so on k minus 1. Hence, by induction hypothesis there exist vectors w1 which is in k lambda 1 dash, w2 which is in k lambda 2 dash and so on wk minus 1 which is in k lambda k minus 1 dash, such that T minus lambda k I raised to mk of V is the same as w1 plus w2 and so on plus wk minus 1. We note that k lambda I dash is contained in k lambda I for I less than k, and T minus lambda k I raised to mk maps k lambda I onto itself for I less than k. Therefore, it follows that there exist vectors Vi in k lambda I for I less than k such that T minus lambda k I raised to mk of Vi is equal to Wi. Hence, T minus lambda k I raised to mk of V is the same as T minus lambda k I raised to mk of V1 plus etc. up to plus T minus lambda k I raised to mk of Vk minus 1, and it follows that V minus V1 plus V2 and so on up to Vk minus 1 belongs to the generalized eigenspace k lambda k. Therefore, there exists a vector Vk in k lambda k such that V is equal to V1 plus V2 and so on up to Vk. This completes the proof. Theorem: let T be a linear operator on a finite dimensional vector space V such that the characteristic polynomial of T splits in the base field F. Let lambda 1 and so on lambda k be the distinct eigenvalues of T with multiplicities m1 and so on mk respectively. For I in between 1 and k, let Bi denote an ordered basis for the generalized eigenspace k lambda I. Then the following statements are true. 1. Bi intersection Bj is the empty set for I not equal to j. 2. B, that is the union of B1 and so on up to Bk, is an ordered basis for the vector space V. And 3. Dimension of k lambda I is Mi for I equal to 1 to k. Mi is the multiplicity of the eigenvalue lambda I. Proof: let V be a vector which is in the intersection Bi intersection Bj, and that is contained in k lambda I intersection k lambda j for I not equal to j. By a previous theorem, T minus lambda I is 1 1 on k lambda j, and therefore T minus lambda I raised to p of V is not 0 for every positive integer p, This contradicts the fact that V belongs to k lambda I, and the result follows. Proof of 2. Let V be a vector. We know by the previous theorem that for I in between 1 and k, there exist vectors Vi in k lambda I such that V can be expressed as this sum V1 plus V2 and so on up to Vk. Therefore, B spans V, since each Vi is a linear combination of the vectors in Bi. Let Q denote the cardinality of B. Then dimension of V is less than or equal to Q because B spans V. Now for each I, let Di denote dimension of the generalized eigenspace k lambda I. Then Q is equal to summation I equal to 1 to k di less than or equal to summation I equal to 1 to k mi, and that is equal to dimension of V. Hence Q is equal to dimension of V, and consequently B is a basis for the vector space V. In part 3, using 2, we see that summation di I equal to 1 to k is equal to summation mi I equal to 1 to k, but it is also true that di is less than or equal to mi, and therefore d must be the same as mi for all I, and therefore we are done. Corollary, let T be a linear operator on a finite dimensional vector space V such that the characteristic polynomial of T splits in the base field F. Then T is diagonalizable if and only if n lambda is equal to k lambda for every eigenvalue lambda of T. Remember, n lambda denotes the eigenspace with respect to the eigenvalue lambda, and k lambda denotes the generalized eigenspace with respect to the eigenvalue lambda. Proof: T is diagonalizable over F if and only if dimension of n lambda is equal to dimension of k lambda for each eigenvalue lambda of T, but dimension of n lambda is less than or equal to dimension of k lambda, and hence these subspaces have the same dimension if and only if they are equal. Our aim is to select suitable bases for the generalized eigenspaces of the linear operator T, so that we may use the previous theorem and obtain a Jordan canonical form. Our aim is to choose suitable bases for the generalized eigenspaces so that we get the desired Jordan canonical form. Now, how to construct or choose these bases for the generalized eigenspaces is the big problem. We will see that starting with an eigenvector, we will be able to define something called a cycle, which is a collection of some very special vectors in the generalized eigenspace. And these cycles will finally constitute bases for the generalized eigenspaces, and they would give rise to the Jordan blocks. Let us see how to construct the cycles and finally create a Jordan canonical basis for an operator T on a finite dimensional vector space. But remember, we always need the condition that the characteristic polynomial of the operator splits in the base field. Definition: let T be a linear operator on a vector space V. V is finite dimensional. Let V be a generalized eigenvector of T corresponding to the eigenvalue lambda. Suppose that P is the smallest positive integer for which T minus lambda I raised to P of V is 0. Then the ordered set denoted by C, which is the collection of these vectors T minus lambda I raised to P minus 1 V, comma T minus lambda I raised to P minus 2 V, and so on, T minus lambda I of V, comma V, is called a cycle of length P of generalized eigenvectors of T corresponding to the eigenvalue lambda. The vectors T minus lambda I raised to P minus 1 V is called the initial vector and the vector v is called the end vector of the cycle. A remark, notice that the initial vector of a cycle is the only eigenvector of t in this cycle. Also observe that if v is an eigenvector of t corresponding to the eigenvalue lambda, then the set singleton v is a cycle of generalized eigenvectors of t of length 1. Let us recall some of the main observations of the first example that we discussed. Suppose that t is a linear operator on C8 and B is the set of vectors v1, v2 and so on v8, which is an ordered basis for C8 such that the matrix representation of T with respect to this basis B is given by these Jordan blocks. So, this is a Jordan canonical form for the operator T. The first 4 vectors of B lie in the generalized eigenspace K1 with respect to the eigenvalue 1, and the vectors in B that determine the first Jordan block of J are of the form v1, v2, v3 given by t minus I square v3 comma t minus I v3 comma v3, and t minus I cube v3 is 0. The relation between these vectors is the key to finding Jordan canonical form. We observe that the subset C1 which is v1, v2, v3, C2 which is singleton v4, C3 which is the set containing v5 and v6, and C4 which is the set containing v7 and v8 are the cycles of generalized eigenvectors of T that occur in the basis B. Notice that B is a disjoint union of these cycles. Moreover, if Wi denotes the span of Ci for I from 1 to 4, then we see that Ci is a basis for Wi and T restricted to Wi with respect to the basis Ci is the ith Jordan block of the Jordan canonical form of T. Theorem: let T be a linear operator on a finite dimensional vector space V whose characteristic polynomial splits in F. Suppose that B is a basis for V such that P is a disjoint union of cycles of generalized eigenvectors of T. Then the following statements are true. 1. For each cycle C of generalized eigenvectors contained in B, the subspace W, that is span of the cycle C, is T invariant, and T restricted to W box C, which means that it is the matrix representation of the restricted operator with respect to the cycle C is a Jordan block, and part 2 says that B is a Jordan canonical basis for the vector space V. Proof of 1. Suppose that the cycle C corresponding to lambda has length P and V is the n vector of C. Then C can be written as V1, V2 and so on up to Vp, where Vi is T minus lambda I raised to P minus I of V for I less than P, and Vp is equal to V. We have T minus lambda I of V1, which is T minus lambda I of P minus I minus 1 of V, and that is Vi minus 1. Therefore, T maps W into itself, and we see that TW box C is a Jordan block. We can repeat the arguments of 1 for each cycle in B and finally obtain the matrix representation of T with respect to B. With the help of the following theorems that we state below, we will see that a Jordan canonical basis is nothing but the union of disjoint cycles of generalized eigenvectors corresponding to the eigenvalues of the operator. So, first theorem says that let T be a linear operator on a vector space V and let lambda be an eigenvalue of T. Suppose that C1 and so on Cr are cycles of generalized eigenvectors of T corresponding to lambda such that the initial vectors of the Ci's are distinct and form a linearly independent set. Then the Ci's are disjoint and C, which is the union of C1, C2, Cr, is linearly independent. And then the corollary says that every cycle of generalized eigenvectors of a linear operator is linearly independent. That is clear from this theorem. And the second theorem says that let T be a linear operator on a finite dimensional vector space V and let lambda be an eigenvalue of T, then K lambda has an ordered basis consisting of a union of disjoint cycles of generalized eigenvectors corresponding to lambda. Let us look at this example where A is this 3 cross 3 matrix whose first row is 3, 1, minus 2, second row is minus 1, 0, 5 and the third row is minus 1, 4. Then the characteristic polynomial of A is Pt, which is t minus 3 into t minus 2 square. Hence, lambda 1 equal to 3 and lambda 2 equal to 2 are the distinct eigenvalues with multiplicities 1 and 2 respectively. Then dimension of k lambda 1 is 1 and dimension of k lambda 2 is 2, because the multiplicities are 1 and 2 respectively, and we know that dimension of the generalized eigenspace is exactly equal to the multiplicity of the eigenvalue. Now, the eigenspaces n lambda 1 is kernel of t minus 3i and that must be the same as k lambda 1 in this case, and the vector minus 1 to 1 is in n lambda 1. Therefore, B1 given by this singleton minus 1 to 1 is a basis for the generalized eigenspace k lambda 1. Since dimension of k lambda 2 is 2, therefore, a generalized eigenspace has a basis consisting of union of cycles of length 1 or a single cycle of length 2. These are the two possibilities. Now, we see that the first case is impossible because the vectors in this case would be eigenvectors, contradicting the fact that dimension of n lambda 2 is 1. Therefore, the desired basis is a cycle of length 2. A vector V is the end vector of such a cycle if and only if a minus 2i of V is not 0, but a minus 2i square of V is 0. And a simple calculation shows that these two vectors 1 minus 3 1 and minus 1 2 0 is a basis for the solution space of a minus 2i square x equal to 0. Now, choose a vector V in this set so that a minus 2i of V is not 0. The vector V given by minus 1, 2, 0 is a candidate for V, and a minus 2i of V is the vector 1, minus 3, minus 1. Therefore, we have a cycle of generalized eigenvectors given by a minus 2i of V, V. That is the set of these two vectors 1, minus 3, minus 1 and minus 1, 2, 0. Then B, which is a set of these three vectors minus 1, 2, 1, 1, minus 3, minus 1 and minus 1, 2, 0 is a Jordan canonical basis, and the Jordan canonical form for the operator is J, where you can see two Jordan blocks. One is that 1 cross 1 block given by 3 and the other one is 2, 1, 0, 2. We have learned that cycles of generalized eigenvectors finally give rise to a Jordan canonical basis. Now the question is how to find those cycles, and we will see in the next module that the computation is somewhat difficult, but of course we will be able to design a strategy which, if followed, would finally lead to the Jordan canonical basis and the Jordan canonical form for the operator T.